Hello everyone, my name is Yunfeng. I'm a graduate student from Fudan University. The topic of my presentation is an accurate and cost-effective approach towards real-time eye movement angle estimation. My presentation will include these four parts. First, the background of our research. Second, the EOG signal acquisition experiments we design. Third, the method of EOG signal pre-processing and the gaze angle estimation model. And the last, some results and conclusions we have got. Firstly, I would like to introduce the background of our research. EOG is a reliable and non-invasive technique which can measure the electrical potentials between the cornea and the retina changes when the eyeball rotates. By placing a pair of electrodes either horizontally or vertically around the eyes, these potentials can be recorded. The transitions and the magnitude of the obtained potentials are essentially corresponding to the rotation angle of the eyes. Thus, EOG has been widely explored in many health applications, such as wheelchair guidance, human-computer interface, fatigue detection, and so on. While for these applications, eye movement angle estimation is considered to be the fundamental step to estimate the eye movement angle. Various approaches have been proposed. These approaches can be roughly classified into the physically driven white box method and the data-driven black box method. A physical-driven white box eye movement angle model, by employing the EOG battery model and the spatial geometric relationship between eye movement and the angle of gaze location. However, the model requires a certain amount of trigonometric function operations. As a result, the model training is resource-consuming. Compared with the white box idea, data-driven black box technique tends to have higher accuracy. Research under this idea normally employed data-driven modeling methods and establish regression models between the eye movement angle and the collected EOG signal. According to the type of the proposed regression models, it can be divided into linear models and nonlinear models generally. Nonlinear model has higher accuracy but requires higher computing resources to train the model. The linear model is a simple model and the requirements for computing resources are relatively low, but its accuracy for large eye movement angle is not satisfactory. To address the above issues, an accurate and cost-effective model based on nonlinear polynomial regression for eye movement angle estimate is proposed. The model is simple, analytical, fast, and with few parameters. Compared with most of the existing methods with high computational complexity, the proposed model can be easily deployed in the embedded platform or mobile device for real-time eye movement angle estimation. Secondly, I would like to introduce the experiments we designed. In this work, EOG signals were recorded for 19 subjects. PSG with denoted filters was applied for the EOG data acquisition. The electrode configuration was set as shown in figure. After that, the subject was asked to make circuits according to the experimental requirements. The circuit's procedure is shown in the figure. The simple theta is the angle between the center point and the target point of circuit. The circuit's sequence is also shown in the slide. At the beginning of the circuit procedure, the subject was asked to gaze at the center point. Then the subject was asked to make circuit from 0 degree to 10 degree, according to the audio prompt of program, and keep gazing at 10 degree point for 3 seconds. At the same time, the program marked the circuit signal for subsequent signal processing. The subject was required to repeat the above process until all circuit sequence has been completed. Finally, we got all circuit UG signal from one subject. Okay, now we move to the part of method. Before building a model, the raw data need to be pre-processed. The data pre-processing flowchart is shown in the figure. We extracted the data between the begin mark and the end mark in the EOG sample as circuit events. Then, we exclude the abnormalities according to the experiment log. After the data were captured, the measured EOGs was manually examined by employing the wavelet transform denoising and observation. Abnormal signals with large noise components was excluded. To build a simple mode between the absolute eye movement angle theta and EOG information, we define the value delta EOG, where the delta EOG is the maximum absolute EOG value after differencing the two electrode EOG signal in absolute eye movement angle. Finally, we obtained the 18 subjects delta EOG data with eye movement angle label. The next is modeling. Traditional eye movement angle estimation model consider eye movement angle to be a linear relationship with EOG. However, some further studies point out the relationship between eye movement angle and EOG is not completely linear, but approximately linear within a certain range. In this work, we build a polynomial model to represent this incomplete linear relationship. Denote the mode as this. Theta hat is the function of delta EOG and W. W is the weight coefficient vector of the polynomial model. K is the order of polynomial model. And the loss function is shown in the next. It is the sum of square of errors. We use MATLAB to optimize the function to get the minimum value. Then we get the parameters of the mode. Now we come to the last part, result and conclusion. The figure shows the performance change of the polynomial model from 1 order to 9 order. The performance increased significantly with the increasing number of orders before the third order and reaches the best around third or fourth order. The performance doesn't improve with the order increasing, but the computational resource consumption and the parameters continue to increase. The following Table 1 shows the best results of leave one subject out method. The model is best when the order of the polynomial is 3 and 4. Compared with the two results, the 3-order model is slightly better than the 4-order model without using the outlier excluding method. When implementing the outlier excluding method, the performance of both 3-order and 4-order models are slightly enhanced. Table 2 shows the speed and the accuracy of polynomial model. The linear model can also be considered as a 1-order polynomial model. Fourier model means the model is fitted by cosine and sine functions. As shown in the Table 2, the 3-order polynomial model can achieve better performance in comparison with both linear and other nonlinear methods. In this paper, we proposed a nonlinear polynomial eye-movement angle estimation model. With the optimal 3-order of the model, the estimation error in angle is less than 3.5 degrees within a large space. The model is simple, analytical, fast, and with less than 5 parameters. Consequently, the model can be easily deployed in the embedded platform or mobile device with limited resources to realize real-time eye movement angle estimation for UG-related healthcare applications. Currently, only horizontal eye movement angle was estimated. In further research, we will explore some experiments to collect both horizontal and vertical eye movement data to build a comprehensive eye movement angle estimation model. Meanwhile, to further verify the model, we will deploy it in a hardware system for realizing a real-time estimation. That's all for my presentation. If you have any question, please feel free to contact me. Here is my email address. That's all. Thank you.